class on hardware security. So, today we shall be trying to see how power attacks can be applied on on a primitive which is called as stream ciphers. So, in particular today we shall be talking about stream ciphers and a very important component in stream ciphers which are called as LFSRs or linear feedback shift registers. We shall discuss about like the types of LFSRs which are broadly two, and then discuss about the power attack vulnerabilities of LFSRs. We shall be then talking about Mickey, which is a standard stream cipher, and shall be discussing about the DP attack on Mickey or a power attack being performed on the stream cipher called Mickey. So, to introduce stream ciphers, like block ciphers, stream ciphers are also symmetric key ciphers, where the plain text digits or bits in general are combined with a pseudorandom stream generator or a pseudorandom key generator, which are also called as the key stream generators. So, in a stream cipher, the idea is that each plain text digit is encrypted one at a time with the corresponding digit of the key stream to give rise to a digit of the cipher text. So, typically these when we say that they are like processed in digits, what we mean is they can be bitwise processed or they can be processed in words as well. So, they can be also like maybe processed in bytes or maybe in words. So, often the reason is because we want to increase the amount of throughput that we get out of the stream cipher. So, a stream cipher typically is a very fast primitive and it has got also a lower hardware complexity compared to say block ciphers, and therefore, it finds wide range of applications. For example, the GSM mobile phones use A51 encryptions, and therefore, it is very popular primitive. If you are interested to know more about stream ciphers, then I would ask you to kind of look into this YouTube clip where you can find more details about the stream ciphers. So then what are linear feedback shift registers, which are so the idea is that the LFSR or linear feedback shift registers are a very important component of stream ciphers. So, just to see how an LFSR works, an LFSR as the name suggests is basically a shift cipher which when clocked advances the signal through the registers from one bit to the next most significant bit. That means, as you can see in this diagram, when I am essentially clocking it, then you will find that this essentially shifts, like this bit sequence shifts to the right, for example, in this diagram. But then we need to find out what is the bit that I will feed back, because when the bits are going to the right, then I am getting the output from the right hand side. This is my key stream which is being generated, which will be probably XORed with the message to give you the cipher. Okay. So, now the question is how do you calculate the input bit? For example, what I mean to say is that this is the feedback. This is the feedback that we would like to obtain. So, this is the feedback that you are essentially that we need to calculate, and this is the output that is generated by this key stream generator. So, often you will find that this output is XORed or exclusive OR with a message to give rise to what is called as a cipher or the cipher text. So, this part is called is a very important component of the stream cipher. Often of course, the composition is not so simple as this and may be more involved, as we will see in when we discuss about Mickey. So, now the LFSR essentially one of the most important things is how do you calculate this feedback for the LFSR. And as you can see here, this is my feedback generation circuit. For example, there are some XORs that has been used, and the reason the feedback only uses XORs, okay, this essentially is the reason why it is called as LFSR or a linear feedback shift register. Okay. It's because it has got only XORs, which are linear gates. So, therefore, I mean the idea is that we would like to basically tap out few points from the LFSR state. So, this is your linear feedback shift registered state. So, from this LFSR we basically tap out few points, for example, as shown by the blue or the shaded portions, and then you do an operation which is defined by this feedback circuit, and you create this feedback bit which is basically being fed back into the LFSR. For example, here we are doing an XOR between 1, 0 and 1. So, 1, 0, 0 and 1, and therefore, you get 0. So, therefore, we are feeding back 0 into the LFSR, whereas the other bits are basically just shifted to the right. So, that is the broad philosophy behind how an LFSR works. So now the idea is that LFSRs can be applied for stream ciphers, and therefore it is an important object to study when we are discussing or considering, like how stream ciphers stand against power analysis or DP analysis. So in this paper, and this is a reference that you can see, which was published in Indocrit 2007, you can see a paper which talks about LFSR based stream ciphers are vulnerable to power attacks. So you can look into this and see that there is a claim which we kind of discuss here, which is that which is essentially that the fact that LFSRs are susceptible to power based side channel attacks. Therefore, one can perform a power based attack on LFSRs. So in particular, the claim says that an n-bit LFSR can be completely determined by making ON power measurements. So if you make order n, that is linear amount of power measurements, then you should be able to completely reconstruct the LFSR, meaning the feedback polynomial, which is often essentially a primitive polynomial, okay, can be completely calculated, okay, and in fact, like you can also calculate the number of bits which are there in the LFSR, okay. So you can calculate the number of stages, which is essentially denoted by small n, which is essentially that means, right, you can totally reconstruct the LFSR. So let us consider an example to understand this. Okay, so here is an LFSR which has got 4 stages, as you can see, like stage 0, stage 1, stage 2 and stage 3, and the feedback in this case is just determined by this exclusive OR. Okay, so which basically kind of taps in stage 3 and XORs with this bit to give back my feedback bit. So you can see that this is the corresponding feedback bit that I obtain, right. The feedback bit is again here, and that is basically obtained by this exclusive OR. So this is my like feedback circuit in this case, and the polynomial has been described as 1 plus d to the power of 4. So that basically essentially sets you the polynomial. So the idea is, like if for example, if there is a new polynomial that you want to read, so typically, right, this is how you read it. So the d to the power of 4 is basically the maximum bit, or like since this is a 4-bit LFSR, you can imagine that the bit sequences which will be generated by this LFSR can be enumerated from by 4 bits. So it can be enumerated by like 4 bits depending upon the values of D3, D2, D1 and D0. Okay. So pretty much you can say that these elements are members of GF 2 to the power of 4. Okay. So now, as you know that for GF 2 to the power of 4, right, you can essentially set a corresponding polynomial, say, like for example, if I said 1 plus d to the power of 4, then you can essentially obtain the elements of this field. And in particular, this feedback polynomial is like written as 1 plus d to the power of 4. That is because of this position. So therefore, this stands for 1 position. This position stands for d. Okay, and gradually so on, so on. So basically, right, you basically can depending upon the tap position, the degree or the polynomial will get changed. Okay. So in this case, it is we basically get 1 plus d plus d to the power of 4, which basically is the corresponding, which basically tells me how the feedback circuit works. So now with this background, let us see how the evolution of this LFSR works when we are basically applying clocks to this linear feedback shift register. So let us take this table. So therefore, here is like we basically loaded. Of course, one thing is to be kept in mind that when you are considering an LFSR like this, and if you load all 0 values, then the value remains stuck at 0. So therefore, we will be considering non-zero initial states. For example, if I load it like 0 1 1 0, so this is an like a non-zero initialization which I do to this polynomial, I mean to this LFSR. So this LFSR, because of the choice of the feedback polynomial, which is 1 plus d to the power of 4, stands out to be something which is called as a maximum length LFSR, which means it basically generates a cycle length which is proportional to 15. Okay, remember that the 4-0 state is not a part of this cycle because we are not giving it because it's a self loop. Okay. Whereas, right, if you feed in like 1 plus d to the power of 4 as a feedback polynomial, then all the 15 non-zero states will lie in a cycle, and that is the maximal length cycle which is possible, and that is why this LFSR is also called as a maximal length LFSR. Okay. So, now if I for example initialize it say at 0, 1, 1 and 0, then you can see that I can calculate the corresponding like the feedback, because you can observe that D3, D2, D1 and D0 are the corresponding states, and therefore, when I am XORing, then I am XORing this position with this D0 position. So, basically I am XORing D3 and D0 to get back my feedback value. Okay. So, in this case for example, if like D3 and D0 are 0, so therefore I XOR them and I get 0 as a feedback. So, therefore, next time you can see that 0 is being fed back. Okay. For example, so what I mean is that when I am XORing D3 and D0, I am getting back this feedback value. So, therefore, if I XOR 0 with 0, I get back 0. If I XOR 0 with 1, then I get 1 as a feedback. Okay. So, you can see that here 0 has been fed back, here 1 has been fed back. So, likewise, right, if I XOR 1 with this 1, I get this 0 which is being fed back, whereas for the other positions it is just a shift. So, you can see that these are nothing but essentially shifting of these values. Okay. So, therefore, right, if you do this, then you can see that if I start with 0, 1, 1, 1, 0 and then like proceed like this, then these are the corresponding states that will essentially like emerge one after the other. And now we basically define two variables. So, one variable is denoted as HDT and the other variable is denoted as PDT. Okay. So, what are the definitions of HDT and PDT? So, in HDT we basically calculate the Hamming distance between these two states. So, you can see that these are the two successive states and I calculate the Hamming distance between them. So, for example, what I mean is that if one of these states here, for example, so this state suppose I denote it as STT, okay, suppose I denote it as STT and it migrates to STT plus 1, okay, and in the next clock cycle it goes to say STT plus 2, then HDT stands for the Hamming distance between them. Okay. So, therefore, I can write that HDT is nothing but like the Hamming distance between. So, let me write this as a Hamming distance between the states STT and STT plus 1. Okay. So, this is the Hamming distance between these two states. Okay. So, what I mean is that if I now have got 0, 1, 1, 1, 1, 0 here and the next state say STT plus 1 is 0, 0, 1, 1, then you can see that the Hamming distance is nothing but the changes. For example, here there is one change and here there is one change. Okay. So, you can actually calculate this. So, see that in one state in the first clock cycle it was at 0, 1, 1, 1, 0 and this goes to 0, 0, 1 and 1. Okay. So, the Hamming distance can also be found out in this way. So, if I take an exclusive OR between these bits, then I have got 0 XORed with 1 is 1, 1 XORed with 1 is 0, 1 XORed with 0 is 1 and 0 XORed with 0 is 0. So, the Hamming distance you can say is also the Hamming weight of the exclusive OR between the successive states. So, therefore, right, the Hamming distance in this case is 2. Okay. So, that is essentially written as 2 here. Likewise, the Hamming distance between the clock cycle 1 state and the clock cycles 2 state is also 2, but you can see that between 2 and 3 there are, if I XOR them, I have got 1 here, I have got 1 here and I have got 1 here. So, therefore, the Hamming distance in this case is 3. Okay. So, now I basically observe the Hamming distances in this way. So, one of the motivations of looking into HDT is because, as we discussed, right, when we are discussing about power models, one of the most common power models in CMOS circuits are essentially what are based on Hamming distances. Okay. So, therefore, you can pretty much assume that this HDT is a good approximation of the power consumption of your device. Okay. So, now what we try to see is that we basically introduce another variable, say call it as PDT, and try to observe that whether the HDT changes across clock cycles. So, you can imagine that like if you are basically the HDT is an indication of the power consumption. So, then it tells me that whether the power consumption increases across the clock cycle or kind of remains the same or diminishes across the clock cycle, because in some cases the power can also diminish, as you can see that here the HDT is say 1. Okay. So, therefore, it means that what we are trying to see over here when we are seeing PDT is basically trying to see whether the power consumption kind of remains same or whether it becomes or whether it increases or whether it decreases. Okay. So, the reason, so what we plot in PDT is just the fact like, So, we say that PDT is 0 if the power consumption remains the same, and PDT is 1 if the power consumption changes. Okay. So, that means, right, we basically compare two successive HDD values. If the two successive HDD values are remaining same, then we indicate that by PDT 0, and if they differ, then we indicate it by PDT 1. Okay. So, therefore, right, you can see that since 2 and 2 are same, I indicate as 0, 2 and 3 are different, I indicate as 1, 3 and 2 are different, I indicate as 1, 2 and 2 are same, I indicate as 0, 2 and 2 are again like same, so I indicate as 0, 2 and 1 are different, I indicate as 1, 1 and 1 are same, so I indicate it by 0. Okay. So, like this I continue, because there will be more states in this evolution until you get back to this 0th state. Okay. So, therefore, now we observe a very interesting observation. The interesting observation is this, that if you observe PDT, then this PDT, right, gives you a binary sequence as shown here. This turns out to be nothing but a delayed sequence of one of these states. Okay. For example, in this case it kind of pretty much exactly matches with the D0 state. Okay. So, you can see that here I get 0 1 1 1 0 0, but here I get, for example, for D0 it is 0 1 1 0 0 and so on, which exactly matches with PDT. Okay. So, that means what is the implication of this? The implication is that if I have got a good power measurement, then I can like get an idea about HDT based upon the power model, and therefore, right, if I get to know about HDT and then try to find out a PDT, which is basically a 0-1 decision to know that whether the power is increasing, whether the power is changing or whether the power is remaining constant across clock cycles, then I get one of the states of the LFSR. Okay. So, now if you get the states of the LFSR, okay, so then you basically have we will see very soon that you can actually reconstruct the entire LFSR. Okay. So, now you can probably argue with me that I already have access to D3, right, because D3 is the output of, or maybe D0 is the output of my keystream generator. Okay. So, what I am trying to say is this, that is if I basically see this diagram, then D0 is the output which I am providing. Okay. But note that the attacker may not always have access to D0, because this may be emerged in a big circuit. Okay. It may be emerged into a big stream cipher, or at least this point is not always accessible to the adversary. Okay. But here what we observe is that from the power measurements and from this estimate of the PDT vector, you basically know the values of D0. Okay. And if you know the values of D0, then you can essentially reconstruct the entire LFSR. Okay. So, now so this is a continuation of this evolution. As I said, that you basically go till 15, and you can see that 15 is nothing but 0 1 1 1 0, which means after this cycle repeats. Okay. Again you can see that this 0 4 ones exactly matches with D0. Okay. So, you can essentially prove as well. You can also go to the reference that I mentioned and see the complete proof, where we essentially can argue that this PDT is indeed a delayed sequence of these LFSR states. So, now what we do is we basically apply a result which is essentially called as the Berlekamp-Massey algorithm. Okay. So, this description from the Berlekamp-Massey algorithm kind of summarizes the power of this algorithm. We will not go into details of the algorithm, but you essentially can at this point just concentrate on the implication of this algorithm. Okay. So, the algorithm says that it basically defines something which is called as a linear complexity of an infinite binary sequence. So, which essentially is defined by LF or denoted by LS and is defined as follows. So, the idea is that if S is a 0 sequence, something like S equal to 0 0 0 and so on, then you can immediately then we define LS to be 0. Okay. On the other hand, if no LFSR generates S, then I say LS to be infinity, which means that no finite linear feedback shift register can generate this sequence. Okay. On the other hand, right, if it is otherwise, that means if you have got if it is possible to generate this sequence, then LS stands for the length of the shortest or the minimal length LFSR that can generate this S. Okay. For example, in our case, the sequence that we saw essentially was generated by a 4-bit LFSR. Okay. That means, like, if somebody gives you this sequence D0 0 1 1 0 0 0 0 0 1 1 0 0 followed by 0 4 1s and 0 1 0 0 1 0, then this sequence can be generated by an LFSR whose length is 4, and therefore our LS is 4, because it is a minimal length LFSR of length 4 which can actually generate this sequence. Okay. So therefore, right, I mean, the idea is that if T is a finite sequence or subsequence of S of length at least 2 LS, okay, so that means if I give you a sequence of length at least 2 LS, then the Berlekamp-Massey algorithm on input of this T, that is on input of this subsequence, can completely generate this LFSR of length LS, which essentially can be used to generate S. Okay. So that means you, as an attacker, right, you just need an exposure to 2 LS amount of data to completely reconstruct the LFSR. Okay. So that means, right, in our case, if LS is 4, then you just need a subsequence of length 8. Okay. And that should be enough for you to solve the entire the equation sets and kind of reconstruct the LFSR, which means you not only know the length of the LFSR, but you basically, you know, like, can also find out what is the feedback polynomial of the LFSR. Okay. So you can basically find out that 1 plus d to the power of 4 using Berlekamp-Massey algorithm. Okay. So this is a very strong algorithm, and if you are interested to know more about Berlekamp-Massey algorithm, you can go through this YouTube clip, which can basically give you an explains the working principle of Berlekamp-Massey algorithm. But at least for this course, we will be using this Berlekamp-Massey algorithm as a black box, and this is how you can engage it. So what I do in this attack is, now I basically measure the power or the dynamic power at t equal to 0, and then for all the subsequent time instances, I measure the dynamic power. The idea is that if the power of one time instance is not equal to the previous time instance, then I define this PDD dash variable and make it 1. Okay. On the other hand, right, if this is 0, that means that implicates that the power consumption does not change across the clock cycles. Okay. So now I basically take this PDD dash, and as I said, that based on the theory that the PDD dash is nothing but a delayed sequence of one of the states of the LFSR, then I just will try to feed it to the Berlekamp-Massey algorithm. Okay. Now at some point, right, the Berlekamp-Massey algorithm will terminate, and then I exit, which means like I have been able to, you know, like, give enough amount of data to the Berlekamp-Massey algorithm so that it can reconstruct the LFSR. Okay. So therefore the result says that a Berlekamp-Massey algorithm outputs the length of the LFSR and also the feedback polynomial f and also the connection polynomial, which is realized by f. And the initial state can be ascertained by solving a system of linear equations from the previous knowledge. Once you know the LFSR structure, then guessing the input state is just solving solving a system of linear equations. Okay. So therefore we can, you know, like, try to kind of reflect on this point a little bit further based on the fact that there are two types of linear feedback shift registers. Okay. So one is what we have just seen is what is called as a Fibonacci LFSR, and there is another class of LFSR which is called as the Galois LFSR. Okay. So theoretically both of these are isomorphic, which means both these LFSR configurations with the same feedback connection polynomials produce the same output stream, but with time offsets. Okay. So now, you know, like, although from the cryptographic point of view both of these LFSRs are equivalent and you can use one instead of the other, the question is whether they are also equivalent with respect to power attacks. Okay. So just to kind of revise, this is how a Fibonacci LFSR looks like, and this is a more general description of as we have seen. Like, here you have got the end states of the LFSR. So this is denoted from you know, like, if I just write down, right, this is basically the S0 state, this is the S1 state, and so on, the Sn minus 2 states, and this is the Sn minus 1 state. Okay. And then what we do is basically we try to kind of observe the feedback polynomial. So the feedback polynomial is nothing but, as we have seen, right, is an XOR, is just based on XOR. So therefore the only gates which are here are XOR. But then you basically tap out few positions, and these are called as taps, and then you calculate this the output of this circuit and you feed it back. So this is your feedback. Okay. So this particular configuration is what is called as the Fibonacci style of LFSRs. Okay. And this is opposed to what is called as the Galois LFSR. Okay. In the Galois LFSR you do this. So you have again this n states, as you can see, like from S0 to Sn minus 1, but now the feedback is done in a slightly different way. Okay. So you can see that what we do here is that the feedback is now kind of put across every like at every stage. For example, this is one stage, like this is another stage and so on. Okay, so these are all the different stages, and you basically like try to find out, you basically tap out, like these are your tap positions, and depending upon the feedback polynomial, you AND it. That means you enable that switch or you disable that switch. So basically either you allow this feedback to pass or you don't allow this feedback to pass by using this switch. So we call this, say, as a toggle switch, which means that if the toggle is 0, then this path is disabled. Okay, so that means you are not tapping out this position. Okay, so again, like you can essentially draw an isomorphic relationship, which means that for every Fibonacci LFSR you can write a Galois LFSR, and also for every Galois LFSR you can write a feedback, like Fibonacci LFSR. Also note that in this diagram and also in the previous diagram, we basically define what is something which is called as a nonlinear Boolean function. So typically what is done is, like based upon these these bits that essentially are over here, we basically combine them by a nonlinear nonlinear Boolean function, and then produce this key stream which is XORed with the plain text to give you the ciphertext. Okay, so this is the kind of model that we compare with, and the question is, right, that the question that we try to address in this discussion is whether these two things are equivalent. Okay, so that means we basically try to consider that whether Fibonacci LFSR and the Galois LFSR are equivalent with respect to power attacks. Okay, so this we will see in the next class. Thank you.